In this talk, I'll present Fraudbuster, tracking IRSF using blockchain while protecting business confidentiality. I'm Yaron, and this is a joint work with Shuaicheng, Tamraparni, Dasu, Divesh, Srivastava, and Xiong. In a decentralized delivery system, items are delivered through a sequence of handoffs between couriers that belong to different organizations. Delivery failures in such systems can be the result of an error, a malicious attack, or a fraud. When a delivery failure occurs, it is difficult to discover the handoff at which the item was dropped because there is no single organization that tracks all the handoffs. The main goal of Fraudbuster is to track handoffs and provide information regarding where failures occurred while protecting business confidentiality. Our main motivation is mitigation of international revenue share frauds. In an international call, the call is transferred through a sequence of carriers from a caller to a callee. The caller pays to the first carrier for the call, and in each handoff, the sending carrier pays to the receiving carrier for handling the call and passing it on. In IRSF, a fraudster carrier short-stops the call by dropping it and not delivering it further. Typically, a hacker hacks a device of a customer, like a PBX, and generates fraudulent calls to the area where the fraudster carrier operates. The fraudster carrier drops the call and shares the revenue with the hacker. The first carrier loses money because it pays for the service but does not receive any payment from the customer. Telecom companies lose billions of dollars yearly due to IRSF. Discovering the fraudulent carriers could help fighting these types of frauds. However, it is difficult to do so because the investigation requires approaching carriers one by one to reveal the route and discover the fraudster that short-stopped the call. Each step of the investigation is slow and requires human intervention. In this paper, we present a system for storing handoff information on a blockchain. In the case of a decentralized delivery system, like international calls, the blockchain solves the problem of lacking a trusted central database of all the transactions. Blockchains are transparent in the sense that the transactions are visible to all the peers and may be visible to other users. This is desired in some applications like cryptocurrencies. However, handoffs may reveal sensitive business information. Therefore, they should only be revealed when necessary, that is, in the case of a fraud, and only to carriers that are affected by the fraud. In this work, we present 4 confidentiality models where information may be revealed to all the carriers on the route or only to the first carrier. In 2 modes, the entire route of the call is revealed, and in the other 2, just the last 2 carriers. Note that fraudster carriers may record misleading information on the blockchain. Hence, it is essential to reveal the last 2 carriers and not just the last one. In the depicted example, in case 1, carrier 2 is the fraudster, and in case 2, carrier 3 is the fraudster. But in both cases, the last recorded handoff is 2 to 3. The decision when information should be revealed is made by an investigation committee. The committee can be a group of carriers, the blockchain peers, or any other group. The committee is honest but curious, and it should not be exposed to any sensitive information. By using secret sharing, only a group of at least K members of the committee can decrypt information. The details are in the paper. In order to implement all-to-all, we use double encryption. A unique key per call is passed to the carriers on the route. So only these carriers can decrypt the information. The second encryption is by the public key of the investigation committee. The investigation committee does not see any sensitive information because it does not have the call key. The carriers cannot see any secret information that has not been decrypted by the investigation committee. The all-to-first mode is implemented by encrypting the transactions using the public key of the first carrier and another encryption using the key of the investigation committee. The investigation committee is not exposed to any confidential information, and the first carrier cannot see any information other than the transactions that were decrypted by the investigation committee. In the last duel, only information about the last two handoffs is revealed by the investigation committee. In the last two first, only information about the last two handoffs is revealed by the investigation committee and only to the first carrier. Note that this is the most confidential mode among the four confidentiality models. To demonstrate the system, we had to implement a simulation of handoffs in a decentralized delivery system. We used Mininet, which is a virtual testnet for software-defined networks, SDN. Carrier nodes are simulated as network switches. Each carrier has a proxy that records transactions on a blockchain. We used a private version of Ethereum as the blockchain system. We also had an implementation of the investigation committee with a module for revealing information when a call is short-stopped. Next, we will present a brief demonstration of the system. Initially, we deploy Mininet and we generate the nodes and the links between the nodes. This is being generated randomly with a selection of fraudster nodes. We can see here that when the simulation begins, we have carriers with their proxies, where the proxies are used to record transactions on the blockchain. In this case, we see 4 different carriers, and a blockchain explorer allows us to explore the content on the blockchain, because we can also explore the content of transactions. However, this content is encrypted so that no sensitive business information is revealed. We also have a module to conduct or to demonstrate an investigation using Jupyter Notebook. In this case, we can explore the transactions of a call that was short-stopped. A carrier only sees initially transactions in which it was involved. However, when a call is short-stopped, the carrier can initially ask the investigation committee to decrypt handoffs in that call, and then it can decrypt the result of the previous decryption. Only the key of the relevant carrier can be used for the second decryption and revealing the handoff. This can be repeated for several handoffs of the call in order to eventually reveal the route. When revealing the handoffs of the route, the carrier can discover the 2 potential carriers which might have been involved in the short stopping of that call. This can be repeated for several suspicious short stopped calls, and we get statistics regarding which carriers were potentially involved in calls which were short stopped. Here we see that carrier 6 was involved in the largest number of calls which were short stopped, and we can see that indeed carrier 6 is a fraudster carrier. Thank you for listening to this talk. I'll be happy to answer any further questions you may have. Thank you.